Hello students. So, in the previous class we started with the concepts of vector calculus, where we introduced the how to say idea of limit, continuity and differentiability of a vector function. Like we already know those properties for a scalar function. We also prove a very basic result, which is sort of like a generalization from a result on scalar function, which is basically that if you have a constant vector, then its differentiation would be 0, and if you have a differentiation of a vector as 0, then the vector must be constant. So, this is also true for the scalar functions. So, we tried to generalize that result for the vector functions, just to give you an idea that lot of properties from the scalar functions, differentiation of scalar functions would be true for the differentiation of vector functions as well. And today I am going to list some of these properties, and I will try to prove at least one or two results, and I will leave the rest of the results up to you, because they basically involve some properties from vector algebra and differentiation of a scalar function. So, I am pretty sure you can be able to solve the rest of the properties. So, let us start with our first result. I am going to write as our next topic as properties of differentiability, properties on differentiation. Let us call it as properties on differentiation of vector functions. So, the first property is vector functions. So, the first property is for today actually. So, if A is a differentiable function, so if A is a differentiable vector, actually differentiable vector function, differentiable vector function of the scalar variable t, then the first result is d dt of a square equals to 2a dot product with dA dt, and the second result is a dot dA dt is equals to a dA dt. So, this one is actually this here is actually the mod of dA dt, and this one here is also mod of dA dt. So, here mod is basically the absolute value. So, that means a square root of if it has 3 components, then the square root of first component. So, I can write it as a1 square plus a2 square plus a3 square. So, that's what we actually mean by mod of a. So, let us try to prove the first result. So, the first result. So, we have here a square is basically the vector here. So, a square is equals to a dot a. So, that's what we mean by the square of the vector. So, a square is equals to a dot a, which is basically mod of a times mod of a, then cos of 0. So, cos 0 is basically 0. So, that means this is mod of a whole square. So, we can call it as a scalar quantity. So, this is basically a scalar quantity, and if we do the differentiation, then this will be basically 2 d dt of a scalar quantity, because mod will actually convert this whole thing into a scalar quantity, and this will be 2 times mod of a times d dt of mod of a. So, that's the first result, and similarly we can prove the second result as well. So, for the second result we will have So, for the second result we will have d dt of So, for the second result we have d dt of a square equals to d dt of we will have a dot a, and from the product of dot product of differentiation, this will be a dot dA dt plus dA dt dot a. Now, we know that differentiation of vector a square is equals to this here. So, we can use the result from section from part A here. So, the left hand side of this one will be equal to this thing. So, we can write it as 2 times vector mod of a d dt mod of a is equals to a dot dA dt plus dA dt dot a. Now, dot product is commutative. So, this can be written as 2 times a dot dA dt. So, 2 will get cancelled, and therefore, we will have mod of d dt mod of a is equals to a dot dA dt. So, mod of a times d dt of mod of a is equals to a dot dA dt. So, this is what we needed to prove in the second result. You can also call it let us say mod of a is equals to a scalar function small a without any vector notation. So, this a is basically scalar. So, instead of writing mod of a, we can we can replace mod of a by a. So, then in that case this one will be d dt of vector a square equals to 2 times a dot a times dA dt. So, this dot is usually the multiplication dot. So, this is not a dot product. So, a times dA dt. So, like scalar dot, and a dot vector a dot dA dt is equals to a times this is small a times dA dt. This is this scalar function. So, it is better to denote the modulus or the magnitude of this vector by a scalar a, so that there would not be any confusion. However, these properties would still remain true for this vector function a. All right. Now, the next result is, or property 2, let us say, is if a has constant length, let us say constant length or fixed magnitude. Constant length means it has fixed magnitude, then vector a and vector dA dt are perpendicular. So, this is the perpendicular notation, are perpendicular provided perpendicular to each other, provided the absolute or the magnitude value of dA dt is not equals to 0. So, of course, the condition is sufficient as well, necessary as well as sufficient. So, let us start with the fact that the a is constant. So, let a has constant length. So, if a has constant length, then what does that mean? Absolute value of a is equals to, let us say, sum a, where a is a positive real number including 0. So, positive set of where a is a non-negative real number. All right. So, and that is basically a constant. Now, from here we will have vector a whole square equals to a square. All right. And if I differentiate both sides with respect to t, so this will be 2 times a dot dA dt. We just saw that, right, in the previous result. In the previous result, we just saw that if we differentiate, this is basically this mod of a square, and then from there we will basically obtain dA dt, right. So, if I do that, then in that case the right hand side, since it is constant, it will be 0, and therefore, from here we will have a dot dA dt is equals to 0, and this means that these two vectors are perpendicular to one another, because from here we will get mod of A times mod of dA dt, and from here what we will get? We will get mod of A times mod of dA dt times cos of theta equals to 0. Now, A has constant length, so mod of A cannot be 0, because this is positive basically. So, mod of A cannot be 0, and we have assumed that this dA dt, mod of dA dt is not 0. So, this is not 0, this is not 0. So, the only possibility is cos theta equals to 0. So, from here we will get cos theta equals to 0, since mod of A and mod of dA dt is not equals to 0. So, from here cos theta equals to 0, we basically get that theta equals to pi by 2. That means these two vectors are perpendicular to one another. So, therefore, the condition is necessary, and we can also prove that the condition is sufficient. So, let's go to the next slide. So, from here what we basically get is theta equals to pi by 2. So, that means the vectors, so this implies that the vectors A dot A, the vector A and the vector dA dt are perpendicular to one another. Next, we have is other way around. So, let us assume that dA dt, they are perpendicular. So, this is equals to 0, and from here we will get dA dt equals to, we will get from here this will be equal to, if I go to the previous slide. So, this will be equal to A dot vector A dot dA dt. So, vector A dot dA dt equals to basically we will obtain A dot dA dt. So, I will obtain this as vector A dot dA dt. So, from the previous result I can use this here and this here. All right, and this means that I can be able to write this as 1 by 2 d dt of mod of A whole square equal to 0, and from here we will basically obtain mod of A square equals to some constant, and if mod of A square equals to some constant or basically a constant. So, from here we can write mod of A is equals to some square root of some constant. So, this will be again a constant. So, that means if they are perpendicular to one another, then in that case mod of A would also be constant. So, therefore, the condition is also sufficient. So, that means if the dot product, if the dot product is 0, then in that case we can also say that the vector is of constant length. So, of course, this condition is necessary as well as sufficient, provided this is true. All right. So, these were the two basic results that we proved here. We can also try to prove some more results, but I think they are all analogous and motivated from the vector algebra or some differentiation of the scalar functions. So, we will skip those, but I am going to write those properties. So, if A is a differentiable function with respect to t, if A is a differentiable function with respect to say t, then we will have d dt of vector A cross product with dA dt is equals to A cross product with d square A by ddt of vector A times dA dt is equals to vector A times d square A by dt square, mainly because when you take dA dt here, then the two vectors will become parallel. So, this is obviously true. The fourth property is the necessary and sufficient condition. It says that the fourth property is the necessary and sufficient, condition for a vector AT to have constant direction is AT times dA dt equals to 0 vector. So, this is also a nice property for a vector to have a constant direction. So, that was for the constant length, this one is for the constant direction, and this is very obvious to prove. So, you just have to use some derivative result for A cross A, and from there you can be able to obtain this. So, it is really not complicated. I can also list some more properties. For example, if you so if a curve is given by, let us say, RT equals to A constant plus B constant, then it satisfies d square r by dt square equals to a 0 vector. So, this is also not complicated to show. So, you just differentiate with respect to t. So, derivative of a constant vector would be 0, and then you differentiate again with respect to t, then you will have constant vector A, that derivative of that constant vector would again be 0, and then you will basically obtain this d square r by dt square equals to 0. So, like that, if you go through some vector calculus books which I have listed in the references, you come across a lot of results which are basically motivated from vector algebra and differentiation of scalar functions. So, I leave those results up to you for practice, and hopefully I will try to include some examples in your assignment sheets as well. All right. So, next we will practice some problems from vector differentiation of vectors. So, these were some results. Now, we will practice some problems before we move on to the next topic. So, let us practice a few examples. So, example 1, if R t equals to say t plus 1 times I t square plus t plus 1 times j and t cube plus t square plus t plus 1 times k, then find dr dt and d square r by dt square. So, now we are practicing few examples. All right. So, we have a given function, vector function R t. So, let us write the vector function R t again, which is t plus 1 times I, then t square plus t plus 1 times j, and then t cube plus t square plus t plus 1 times k. So, these are all the components along the x, y and z directions. Now, we have to find out dr dt. When we study about application of vector calculus, we will get to know what does this dr dt mean, and also similarly what does d square r by dt square mean. But so far at the moment we will just stick to the basic calculation of dr dt and d square r by dt square. So, this one will be just differentiation component wise with respect to t. So, if I differentiate this one, then differentiation of 1 is 0, differentiation of t would be 1. So, this will be I. Similarly, this will be 2 t plus 1 and this will be 3 t square plus 2 t plus 1 times k, and when I differentiate again with respect to t. So, this will be differentiation, the component of I is 1. So, differentiation of 1 is 0 times I, differentiation of 2 t is 2 and 1 is 0. So, 2 j, differentiation of 3 t square would be 6 t plus 2 times k. So, since 0 times I is 0, so we will not write that component. I take 2 common. So, j plus 3 t plus 1 times k. So, this is the required answer for d square r by dt square. So, that is how you basically calculate the derivative of the given vector function. Let us practice another example. So, suppose if r t equals to, we have sin t times I cos t times j plus t times k, then find dr dt, d square r by dt square, mod of dr dt and mod of d square r by dt square. So, the solution would look like this. Our given function r t is sin t, then cos t times j and then t times k. Now, dr dt, what is our dr dt? So, dr dt would be differentiation of sin t is cos t I, differentiation of cos t is minus of sin t j and differentiation of t k would be just k. So, from here our mod of dr dt would be square root of cos square t plus sin square t plus 1 square. So, square of cos square t plus sin square t would be 1 and then 1 square is 1. So, this is basically square root of 2. And again we will calculate d square r by dt square from here. So, this will be minus of sin t I, then minus of cos t j and differentiation of 1 is 0. So, 0 times k. So, basically minus of sin t I minus of cos t j, and from here we can calculate our d square r by dt square as square root of minus of sin square t plus square root of minus of cos square t. So, ultimately 1. So, that is the required answer, and it cannot be plus minus 1 or plus minus 2 because we are talking about the magnitude, and the magnitude cannot be negative. So, that is why we are always taking the positive value. So, this is the required solution to this problem. All right. And another example of this type could be that you might be asked to evaluate something like this. So, suppose if r is equals to, if r t equals to cos n t I plus sin n t j, then show that r cross dr dt equals to n times k. All right. Or you might be asked to show that r dot dr dt equals to something else. So, here we have r t equals to cos of n t I plus sin of n t j. So, from here we can calculate our dr dt because we are needed to take the cross product with of r and dr dt. So, here dr dt would be minus of n sin n t I, and this one is n cos nt j. Now, we will calculate the cross product r cross dr dt. So, this will be I j k. We know that how we calculate the cross product. So, we take the determinant, and then here we will have component of r. So, cos nt sin nt, and then component of k is 0, and here minus of n sin nt n cos nt times here the component of dr dt, the kth component is again 0. So, if you break this determinant, then you will find that both the components I and j are 0, because their coefficients are 0. So, I and j would not occur, and simply we will have k times n cos square nt plus n sin square nt. So, if I take n common, then this will be cos square nt plus sin square nt. So, that is 1, and therefore, this will be n times k cap, and this is what we needed to prove. So, you might come across examples which are of this type, that you are given a vector function, and then you will be asked to evaluate r cross d square r by dt square, or r dot d square r by dt square, or you will be given an expression d square r by dt square plus r cross dr dt plus r dot dr dt, and then you will be given an expression, or you will be asked to find a certain expression. So, just remember that all you have to do is do some simple differentiation with respect to t of the vector function r, and then just calculate those expressions. So, substitute the values, simplify them, and that will give you the required answer. So, these type of examples would not be that difficult, and I am pretty sure you can be able to solve all of these by doing some simple differentiation. So, we may try to solve maybe 1 or 2 examples more, a little bit different than these in our next class, and I am hoping that you would find them interesting. So, thank you for your attention for today, and I look forward to your next class.